Hello students, in this video we'll prove the polarization identity for a complex inner product space and see an application to the Parseval and Plancherel theorems. So let's let V be a complex vector space, complex inner product space. Then, for any U and V in your vector space V, we have that the inner product of U and V is 1/4 of U plus V in norm squared plus I U plus IV norm squared plus I squared U plus I squared V squared plus I cubed U plus I cubed V squared. That's the polarization identity. So we can sort of see there's a symmetric pattern to it, right? I could have put an I to the power of 0 here on this V, and I would have had really the sum, J goes from 0 up to 3, of U plus I to the power J V squared in norm, right? So this is the polarization identity, right? Excellent. So this tells me if I have a norm identity, I get a corresponding inner product identity for free, okay? Excellent. So let's prove this polarization identity. So what we're going to do is we're just going to sort of slowly break things up, right? I'm going to call this term over here number 1, this term over here number 2, this term over here number 3, and this term over here number 4. So let's do it carefully. So what's 1 equal to? So 1 is equal to U plus V squared, which is going to be what? Which is going to be just U plus V and then U plus V, okay? So this is going to be, if I distribute this out, it's going to be a UU plus a UV plus a VU plus a, let's see, so we have a UU and I need a VV, right? A VV. Great. Those are terms I get. Now remember that for a complex inner product space, we have this identity over here. We have that U. If I want to switch the order, if I have for UV is the same thing as VU with a complex conjugate over, right? So that's one of the rules we're going to use for complex inner product spaces. We have to bear in mind the conjugation rule, okay? Excellent. Let's look at number 2. Number 2 is an I, right? So we're going to have I's with number 2. This is going to be I times U plus IV squared is going to be I, and then a U plus IV, and then a U plus IV, okay? Good. And so what's going to happen over here, this is going to be I times what quantity? I times the quantity UU, so I have a U and then a U, and I'm going to have a U and an IV, so that's, now what can we do with that I in the second slot? The I in the second slot comes out as a negative sign, so that's going to be a plus, a minus I, and then a U and then a V, UV. Then I have these terms over here, so I'm going to pull out an I and then a VU, like that, from those terms over there. And then I'm going to have an IV and then an IV. So what's going to happen over there? So that's going to turn out to just be a what? So IV is just going to be a V squared, right? Because I can pull out one I and then pull out a negative I. So I and then negative I. So maybe we can write that we pull out an I and negative I. So I'm pulling out a negative I squared and then V, like that. Excellent. All right, let's look at 3. 3 is going to be I squared, which is -1, obviously. And then I'm just going to write U minus V because that's what it really is. So this is going to be a negative U minus V and then U minus V. It's a total negative of what? Of UV, UU. That's of course just the norm of U. Then a minus VU, VU like that. Then a UV with a minus sign, minus UV. And then a plus VV, plus VV like that. Over there, good. All right, and then finally 4, right? And so what's 4 going to be? 4 is going to be I cubed, which is just negative I, and then U minus negative I V, okay? And I've just used the fact that I cubed is negative I, okay? This is going to be negative I, and then U minus IV, U minus IV. That's going to be a negative I, and then what? I'm going to have a UU, UU. Then we're going to have a U and then a minus IV, so it's going to turn to a plus I UV, because I'm using conjugate symmetry here. And then I have a minus I VU. And then finally, I have a negative I and then a negative I, so it's going to be a what? That's going to be a total factor, let's call it the cumulative factor over here. So I have a negative I, and I pull out a positive I, so I'm going to have a negative I squared. It's going to be a positive number over there, okay? That's really, so maybe we should be really, really careful about that, just to show that what we're really using here with the v squared. I can pull out a negative I, so I can pull out a negative I. Then I can pull out a negative I, that's a positive I, right? So I have negative I squared, and that's going to be a positive 1, v. Okay? Now I have all the terms just to figure out what's going to happen over here. So let's look carefully over here. So look at these terms over here. I have a UU, and then I have a negative UU over there. So those are going to cancel. And then I have a negative IUU, and then an IUU. So those terms over there are all going to cancel out, right? So those terms are all gone. Let's do the same thing over here with the what? With the V's, okay? What's going to happen with the VV terms over here? So right over here, what do we have? We have a VV, and over here we have a negative VV, okay? Over here we have a what? That's going to be, this number over here is positive 1, right? This number over here is positive 1. I have a negative I and a positive I and a negative I, so the VV terms are going to cancel out over there. Beautiful. And then what terms are left over here? Let's count the terms that we have. So let's see. So I have let's look at these terms over here. These are terms that we actually are going to count over here. So if I add these terms together, so in other words, 1 plus 2 plus 3 plus 4 is going to give me what? Let's look at this term over here. I have a UV. Then over here I have a negative I times positive I. That's going to be a positive 1. That's negative I squared positive 1. So that's another UV. And then over here what do I have? I have a negative. That's going to be another what? Another positive UV. That's 3 positive UVs. And then over here what do I have? I have a negative I and a positive I. That's a positive 1 and a UV. So I have 4 UVs over here. So 4 UV. All right, that's good. And then what are the last terms over here? So let's see what we get for the last terms. The last terms, we're going to have this term over here. That's a VU. Over here, this is going to be an I, and I is a negative VU, so those are going to cancel out. And then we have a what? So we have a positive V over here, and then where's the V over here? It's going to be a negative V. So I have a positive, then a negative, right? So it's a negative VU, so that term over there, and then that term over there are going to cancel out as well. So that term, and that term cancel. And so we have all this cancellation, so we see that I plus 1 plus 2 plus 3 plus 4 is just 4u times v, and therefore we get our polarization result. So this implies that 1/4 of I plus 1 plus 2 plus 3 plus 4 is just going to be equal to uv, and we have our polarization result. So that proves polarization. Now, as a consequence of this, what do we know? As a direct consequence is we know that 1 over 2 pi, the integral from negative pi to pi, of f of x squared dx is equal to what? Is equal to the sum over n and z of what? Of n and z of f hat of n squared. This is just our Plancherel theorem, right? This is Plancherel. Okay. Now, Plancherel is a norm identity, right? This is just the norm that we have an inner product space over here. So by polarization, so polarization implies that 1 over 2 pi, the integral from negative pi to pi, of f of x times g of x complex conjugate, that's my inner product, is going to be the sum over n and z of what? Of f hat of n, g hat of n, complex conjugate, and that's our Parseval theorem, right? So our Parseval theorem actually comes from the Plancherel theorem in polarization. This is true for an arbitrary complex inner product space. So this is our Parseval theorem. So we're able to use the norm equality to get an inner product inequality by the polarization technique. Thank you very much.